Greg Sheldon here, your host of Metal, Steel, Manufacturing, and Business Pro podcast, where you learn everything about the metals and manufacturing industry that make your modern day life possible.
Very nice to be back.
Thank goodness, because he's got such good information to get. Because we do a lot of business stuff on here, and I bet you some of the listeners are getting tired of hearing about the business stuff. So we're going to actually talk about metal today. So we discussed talking about material selection, and that is definitely something that happens in the world, right? Definitely in material science. So
yeah, absolutely. I mean, someone say it's our bread and butter, right? Everything that's made that has a metal in there, someone had to make a decision and say, hey, we're going to use this metal. There's a reason for it.
do you think there's always a reason though?
Yeah,
Other than cost.
Yeah, absolutely. I mean, even if it's plentiful.
Oh, okay.
Right? We have 1040 steel in the shop. Let's try that out, and then they just never change it. That's a reason.
Yeah.
But cost is one of the big ones. Cost and properties, I would say are probably the two biggest reasons.
Cost and okay. So availability. So like steel, like iron is readily available, right?
Yeah, I mean, steel is cheap, versatile, comes in as many flavors as you can imagine, and did I mention cheap?
Yeah, you did. So what would be a reason to choose? Okay, so when it comes to your mild steel, like your 1018 or 1020, you're going to use, that's what you would use for, what would you use that for? Would that be like sheet metal, and then you've got your other grades for structural stuff?
Sure. I mean, the thing about steel in particular, so let's back up for a second, talk about material selection, and we'll come back to steel in a second.
Okay.
So, you're faced with a choice, you're making something. What are you going to make it out of, right? So if I'm a designer, I start looking around, what do I need out of my product? Are there very specific properties I need? Is there a property that's going to be the keystone for the whole thing? If I need this to be electrically conductive or thermally conductive, that's what this whole thing is based on. Then that's kind of at the forefront. If I need strength, then that's what kind of strength, as we've talked about before, and then how much. We've talked about even narrowing it down to, let's say, tensile strength. We want it to be high strength. Well, what is high? Give me a number. Let's put a number on. So we really have to identify what the properties are that you absolutely need, and then how we're going to get there, right? Can I make, I know we've alluded to it a little bit in the different processes, but does it need to be forged? If the material I'm selecting is best as a casting alloy and needs to be forged, then maybe I need to go back to the drawing board. So can I make it in the kind of shapes that I need to? Is there another way to make it? And then, am I willing to pay the cost it's going to take to get there? With steel, sometimes it's good enough. And as a metallurgist, I've been asked before, well, what's the best material you can make this out of? And there is probably an answer that is not steel or something, a common alloy. The question is, are you willing to pay the cost to get there? Let's talk about automotive. Formula One, everything's carbon fiber or titanium or very specialized stuff. They're willing to pay that cost delta.
Yeah.
Right. You can give your the car in your driveway F1 performance if you're willing to replace all of the parts with lighter, stronger, better materials. And that's what they do if you watch something like the Grand Tour or Top Gear, they test drive the really fancy models, and then they start talking about, well, they replaced the hood with carbon fiber and the pistons are titanium now, or whatever it is. So yeah, you can get better performance. Um, Driving out of the roads, do you need that? Maybe,
Exactly.
maybe not.
It depends.
Do you want to pay the extra 50K for premium materials? Maybe you
And
do.
yeah, in that scenario, and it does probably apply to everything else, is like what's important, right? Like,
Mhm.
do you care about what you're driving? I mean,
Yeah,
let's say I don't care, then I'm gonna drive a K car. Or, well, K cars, nobody below the age of me would know what that is, but like a Honda Civic, just a basic Honda Civic could get you
sure.
there versus but what's important, right? So yeah, that's smart. So you start with a checklist, I guess, and you prioritize what's
Yeah, and depending on what you're making, it may not be that organized, right? You may not be, if you're not in an industrial setting, you may not be looking at books full of properties and saying, well, I need to hit 150 KSI, so these are the materials that are available. It may, like I said, if you're making something at home, out in your workshop, it's, well, I got some bar stock over there, and that steel should probably hold. That'll be good enough.
yeah.
So again, I think material selection is a great example of what metallurgists do, and in an industrial environment, because in school you never learn about cost, right? Or it's not brought up. That's not part of the curriculum. Some professors will talk about it, and that's the biggest surprise for engineering students when they get out into the world. You're doing engineering, yes, but also better keep in mind cost reduction and cost avoidance for your projects. So, material selection right from the start, you're baking cost in with the process you're going to use, the materials you're going to use, and it's such a factor. If I need these better properties, I have to pay the cost.
Yeah.
Um, If I want planes to fly, I need single crystal turbine blades in the back half of the engine. Um, that costs a certain amount of money.
Yeah, absolutely. And but again, it also depends on the buyer, right? Like the new Tesla, whatever truck, whatever you call that truck, has a stainless steel body on it, right?
Yeah, the DeLorean flashbacks over here.
Yeah, absolutely, right. And I mean, it's cool looking, but I don't know the price tag on that thing. I'm guessing it's not cheap. But is that really necessary? Probably not.
I think everyone
Um,
gets by with paint just fine.
yeah, exactly. Paint and plastics
Mhm.
and aluminum. So I guess I mean Ford has switched a lot to aluminum, as a
Well,
for
let's talk about that. So that's a great material selection project right there. So
yeah.
everyone's been getting by with steel and plastics in some of the uh, some mid-sized sedans. Back with Saturn, you start seeing the advent of plastics and dent-free doors and all that. Steel is dense; it's heavy.
Hmm.
You have a density approaching between 8 and 9 grams per centimeter cubed. Aluminum's in the 4 and a bit range. So I mean that's a half. You know,
Yeah.
um, I'm sorry, I think aluminum's even lighter. I'm thinking titanium is in the 4 and a bit range. Um, so you have what's been going on to spur the change, right? Steel's been good for forever. You have emission standards. Um, the CAFE standards are the strictest, and you have to hit the numbers, right? So there's your genesis for properties right there, and then what are the levers you can pull? The internal combustion engine can only be so efficient to push mass around. So what does Formula One do? What does NASCAR do? Weight, right? So if you replace steel with aluminum, you're cutting a ton of weight, and you can once you cut that, you can downgrade some of the other things. So by making that one choice, replacing a lot of the structure with aluminum, you're cutting weight, and then you have a lot of other things you can play with, decisions to make to hit the emission standards.
Yeah.
So there's a policy that is, an engineering problem. Hey, you need to hit this miles per gallon, and then turn it over to the engineering staff, and how are we going to get there?
Yeah. Yeah. So reduce the weight, which reduces the carbon emission because the engine doesn't have to have as much horsepower, right?
Yeah, I imagine it has, I'm not a car expert, but I imagine that has a whole other host of things, just like in an airplane engine. You start cutting weight there on a rotating component, then you can make the shaft smaller, you can decrease the forces. There's a whole host of benefits that go along with that.
Well, and decrease the cost too, I would think. But I guess maybe if your materials are changing, so you're getting narrower shafts, you have to compensate for that somehow, right?
Sure. There's this is where material selection is fun. You change one thing, okay, well, now I can change all these other things, and kind of opens it back up again. So things that were settled, now maybe I'm doing different things. Now maybe I need other new materials.
Yeah. Cool. So what are some of the common types of materials in aerospace? Like you've got your superalloys, right?
Yeah, I know we talked about that before. That's my specialty. Yeah, nickel-based superalloys. You have nickel iron superalloys and cobalt superalloys.
Okay.
Those are all kind of fulfill the same function: high temperature creep resistance, great corrosion resistance. You see that in the hot sections of the turbine. Although nowadays you're starting to see some new materials creep in. Materials that are actually in engines. There are intermetallics. There are thialuminides. So titanium and aluminum in stoichiometric ratios. And they have the density of a ceramic. So they're light, maybe in the 1.9 to 2 point something grams per centimeter cube range, and the temperature resistance of the ceramic. But they also have the brittleness of the ceramic.
Right.
So that they're in the back half of the GE NX engines.
Okay.
So they're in jets flying right now.
Yeah. Okay. So let's talk about some of the terminology. I think we've done this before, but let's do it again. So you've got your hardness, your toughness, your ductility, you've got your brittleness.
Sure. Yeah.
I mean, how do all of these things relate when you're talking about materials? Like if I was to say, like that thing that we were talking about that nobody knows about is this heat or temperature change cycle, right? That reduces or increases the life of the product. What is that doing? Is that creating a hardness? Is that creating a toughness? Like, how do you define these things?
Sure. Yeah. I think we alluded to before, strength is a pretty generic term. It's in everyone's lexicon, so to speak. Something is strong. It's an evocative term, but it's not a descriptive term. For us as materials engineers, material scientists, these terms relate to specific properties. So there is tensile strength, yield strength. Those are both properties determined from a tensile test. So we can test a material and get values for these properties. The yield strength is the point at which a material begins to yield or you switch from the elastic deformation region to the plastic deformation region.
Okay, so
Oh,
that means
yeah. Let me put it in a different way.
okay.
Everyone who's ever dinged their car door knows that there are two types of dings, right? The one where you carelessly open your door and hit a shopping cart, and then you look at your door, you're like, wow, that didn't do anything. I thought I heard something, but nothing happened. That's elastic deformation, so it's totally recoverable. It's fine. If you stretch something to under the yield strength in a tensile test and let go, the strain will recover. And then there's the plastic deformation where you open the door and there is a new dent in your door. That's what we call plastic deformation. It's permanent deformation. It's not recoverable without some processing. So the yield strength is the strength which is required to permanently deform the material.
Okay.
So that's a measurable property, and that's one that we designed to. So if you need your widget to not deform, you want to stay below the yield strength.
Okay. Okay. So what kind of processes, like when it comes to treatment of like, okay, so let's say you get into the plastic deformation.
Mm-hmm.
That could be caused by, could it be caused by welding, for example, or, external forces, or I guess they'd be internal forces. It depends on the nomenclature,
the nomenclature there. So
or the semantics, I guess. Like, is it welding isn't, it's external, but it creates internal forces.
Sure. I mean, welding is at its heart a joining process. I mean, you're talking about fusion welding for the most part.
Yeah.
So you're joining two materials. There's some melt of the materials plus a filler or weld wire to join the materials together. You're not really creating any deformation, so to speak. What you are doing is creating stresses. So we can talk about stresses as either mechanical or thermal. There are a couple others, but let's leave it at those two. So the dings in the car door would be mechanical stresses.
Okay.
So I physically do something to the material to deform it. I twist it, I bend it, I pull it, I compress it.
Yeah.
Those create mechanical stresses. Thermal stresses would be caused by thermal cycling, going hot and cold reactions. If you have an aluminum pan where the handle gets shaky, after a couple of years you can rattle it around. What you're seeing is the effect of thermal cycling. Aluminum and the steel of the handle usually have different responses to temperature.
Right.
And after so many thermal cycles, the once tight bolt hole for the handle has changed size, let's say.
Right.
So thermal cycles. Anyone especially up in your neck of the woods knows not to put hot water on a cold car window, right?
Well, there is an interesting phenomenon, and I don't know if you know the science behind it.
I'm from Florida, Greg. Enlighten me.
No, I don't know. I'm going to ask you, why does hot water freeze faster than cold water? And this isn't a joke or a setup for a joke. I'm curious.
Yeah, no, I'm afraid I'm a little bit too far from physics to
I thought you might know.
and too little practical experience with the cold to answer that one. Maybe one of your listeners can chime in at some point.
That would be awesome.
Tell us both.
The
only cool I can tell you about the another cool cold effect, the Leidenfrost effect. This is how you can put your hand in a and I strenuously do not recommend trying this at home, but it is a thing you can do. It is a scientific based. You can put your hand in liquid nitrogen, the speed at which you do it can create a vapor barrier, which will
Oh,
prevent it from hitting your skin. So it is called the Leidenfrost effect. There is a scientific name and purpose for it, but I'm sure you can find a YouTube video which demonstrates that, and I heartily recommend not
here comes the lawsuits.
recreating it.
No, the same will happen with heat too,
Yeah,
from
you
my
know,
understanding.
yeah, it's a vapor effect. So whether it's the steam of heat or the what's going on with supremely cold material,
Mhm.
um, it's the same thing. But getting back to thermal stresses, repeated heating and cooling creates stresses just the way mechanical uh, cycling would as well. So,
Okay, so
the,
because the heat of the weld, right? Like the metal shrinks when it cools, right?
yeah, yeah,
Um, is that exclusive to metal?
it's um, it's not, but water is the
Is
opposite.
as the opposite?
So that's one everyone thinks about.
Okay. So yeah, so the metal shrinks when it cools, when the weld cools, which
Right, and
pulls
that's how
it.
you can get cracking.
Yeah, yeah. So
So with welding, you have your heat affected zone, right? The area around the weld where you can absolutely ruin your heat treatment if
uh,
uh, if you're welding, depending on the kind of welding, how good of a welder you are, how long you're on target, right?
sure.
Um, if it's heat treated a specific way, and specific, I don't mean they're heat treatments that are you're going to lose welding. What I mean is that it depends entirely on temperature and material. Um,
Well, the welding process too, actually, because
sure,
there
sure,
are different processes that have a smaller heat affected zone than others, right?
yeah, yeah,
So,
depending on the heat source and all these other things, absolutely. Um, So, your heat affected zone could ruin your temper on your steel, let's say. Um, you could also, if you have a forged material and you're welding it together, if your weld isn't, if you're using one of these weld processes that creates a wider heat affected zone or a wider melt pool, then you have your two forged materials that are connected by a material that more closely resembles a casting. So there's a property difference there.
yeah. Do you guys do much of that, like in school with material science? Do you guys talk about welding much?
Some it highly depends on the school. Material science is such a niche major. I was speaking of this with a professor at Oregon State the other day. The what kind of material science school it is highly depends on who the professor is. For example, Ohio State is widely recognized as a great welding school. They have the Edison Welding Institute there, and they recruit people who get involved in job research welding. So um, there are a couple schools that do superalloys very well. Um, my professor at Florida, Dr. Fuchs, just retired. We had a reputation as one of them, and Michigan under Teresa Pollock was, and then she moved to UC Santa Barbara, so then they became a great superalloy school. Sammy Tin and a couple others moved to Arizona State, and then they became a great superalloy school. So it's such a small world that it highly depends on who's doing research where. Um,
Good. Yeah, and probably the community affects that too, I would think. Like what's the major industries in that community? I'm guessing. I don't know.
yeah, yeah. I mean, it all has an effect.
Yeah.
Who's getting what grants and what
Yeah.
industries support you know the the industry supported research that's being done. Yeah, it's all important. but yeah, the welding's a big part of it, but it's one of those things that there is research done, but a lot of it is not um, not as much in the schools, at least the teaching of it, because you have to understand the basics, and that's what the schools are about. I mean,
Yeah.
engineering school teaches you how to problem solve and the fundamentals you need to hit the ground running when you get a job. A lot of it's on the
Mhm.
job training, which no longer exists.
Oh, really?
Yeah, at least in my experience.
Okay. So
You have to be a self-starter. You have to,
yeah.
um,
So what about this cost stuff? Like when you say you don't learn about the costing in school, but maybe that's maybe there's some kind of opportunity there for the schools to do that, but maybe a guy like yourself, I have no idea. I'm just thinking out loud, like that is a huge thing. Obviously, you're going to work for corporations or conglomerates that care about that sort of thing. So I don't know if that's
if you have great professors, then you do learn about it. We would sometimes stop in the middle of physical metallurgy class, and someone asks a question, and he's like, okay, this is important, we're going to talk about this, and we're going to talk about the the way the aerospace industry works with the three primes and suppliers and stuff. That's more important than what was on the syllabus for today, so let's sit and talk about that.
got it.
But I mean, the academic environment depends, because a lot of professors are there to do research, and that's fine, but the system's been set up in a way where they need to be successful research and bring in money to be on the tenure track and all that, and there's not as much an impetus to be a excellent teacher. So you get taught by TAs or teachers who would rather be doing research and are better at research. Some of them try, they're just not great teachers, which is not a sin in of itself, but is tough when you're taking the class and have to get a grade on it.
Yeah. Yeah.
So really great teachers or mentors will kind of clue you in on that. Also, it's why internships, co-ops are valuable. You kind of learn, you get a sense for that kind of thing early on. But if not, you will learn it in once you get into industry. But it is important. But when you're talking about let's go back to material selection. In material science engineering school, right? As a mechanical, you may have kind of a design capstone where you have to design a new mechanism or create a product or something. For us, we have material selection capstones. So come up with an idea for something, then go through a number of exercises to figure out what kind of material you use for it. Cost was sometimes part of it, but it also, as a student, it's hard to find out what things actually cost.
Oh, okay.
Sure, I can buy I can get the cost of a ton of stainless steel from wherever. I can find that commodity cost, but
Mm-hmm.
something that's specialized, how do I figure out what the final cost of a part is that I bought, did a bunch of processing to, and then have a final product, right? How do you quantify that cost? You can estimate for sure, but that's part of the reason why cost isn't as big factor in in these kind of internal design projects, because it's materials, the information is just not readily there. Whereas if I'm working for a company, I can go to a procurement person or supply person and say, I need this material, and I can get a cost per pound, because that's their job, and that's they're going to their supplier and saying this
Got it.
is what it costs. So then we can quantify that. This is, if we're doing this internally, it costs this. We're doing this externally, it costs that. So
Mm-hmm.
I think just raising awareness and understanding that how big of an effect it's going to be. just like they don't tell you how important your Microsoft Office skills are going to be if they were really trying to benefit their students, you'd have a class that's just on Microsoft Office or Excel.
Yeah.
At certain workplaces, you wouldn't be considered a good engineer unless you could reliably use a pivot table or a VLOOKUP table.
Mm-hmm. Mm-hmm.
If you don't have the skills, it's like, well, you're just wasting your time.
Yeah, that's not good.
I'm joking a little bit.
Well, I didn't know, but at the same so you pick up on those things along the way, right?
Yeah, going back to material selection is all about, like a lot of things, it's about boiling down your choices and then deciding what the most important factors are. That's it at its essence, right?
Yeah. Yeah.
And it's important to have people like me who can say, well, you think that this property is the most important, but actually we should be concerned about this, and I'm really worried about how we're going to make it if we use this material. Do we want, there's a whole market of, look around at commercial goods, right? Golf clubs, baseball bats, things like that. How much of that marketing is aerospace grade aluminum, lighter, faster titanium, and it's not needed, but it can be made out of it and sold at a premium.
Right.
So there's your cost ratio right there, right? It's I'll use an example from my own childhood. So I played lacrosse as a kid. And I didn't realize I was going to be a metallurgist yet, but I should have been clued in because I was really fascinated by what the lacrosse shafts were made out of. And they have great marketing teams.
Yeah.
There's ultra alloy and and these have great names and cool coatings and graphics and stuff. And then I was sitting at a conference and I was like, I haven't thought about it in years. What is all that made out of? And it's all 70-75 aluminum, 60-65, it's like 3 different aluminum alloys, and it's all the same stuff. They just slap different logos and stuff on it. The ultra alloy shaft was my favorite, and it was gold. Looked so cool, right? It's the same as something else. And then people had titanium shafts, and did you need it over aluminum? No, but the walls are thinner because it's stronger. So I had a coach who used a wooden shaft, right?
Okay.
A friend who had carbon fiber. It's like, is this stuff necessary? Absolutely not. But someone's making it and selling it. Right?
Yeah, exactly.
And it was cool. It was super cool to 10, 12-year-old me. So I should have figured out it was a metallurgist early on if I had known what they were, right? So
yeah, exactly. Yeah. Well, it's funny. It's like the things, once you start to dig into things, like anything, it's not as glamorous as it once was. It's like,
I swear every workplace I've ever been at, I'm like, how do we even make product? Everyone else has got to be better, right? They've got to be more organized or have better systems. And you go somewhere else, it's like,
no, it's the same thing.
No, it's the same thing. Everywhere's just people doing the best they can.
That's all it is, man. Yeah. And we all make mistakes, and we get up the next day and move forward and try and do it better the next day. But sometimes it's worse.
Yeah. Well, I want to give your listeners more information about material selection. I want to get back to and talk a little more technical stuff. So, if we talk about engineering materials, right, we have copper, aluminum, steel, stainless steels. We'll keep that as its own class. Magnesium, if you want to be fancy, superalloys, and think about what the kind of defining trait of each of those materials is and why you would use them. Steel is cheap and heat treatable to nearly any configuration. I can make very strong, so I can make high tensile strength, high toughness. I can get it very hard. I can get it very sharp. I can take the same steel and heat treat it to be as sharp as a kitchen knife or as tough as a machete. Stainless steel comes in a lot of different flavors as well, and the difference there is you're adding chromium for corrosion resistance. So you'd use a stainless steel if you care about looks, you want it to be looking pristine, or if you're working in a marine environment or an industrial environment.
Mm-hmm.
I wouldn't use steel to make water bottles, but there are a ton of companies using stainless steels. You could use titanium for the same thing, but the price would be unappetizing to the consumer. You can use aluminum, but you have to coat them on the inside, which wears away. So
why do you have to coat it?
Because the oxide layer isn't as good. The protective oxide layer, the aluminum oxide, is not as nice for the application as chromium oxide.
Okay.
So, that's why if you get a free water bottle from something, it's probably aluminum because it's the cheapest. You hardly ever see titanium, although they do exist. And stainless steel ones are very nice. You can have a vacuum sealed stainless steel water bottle for a reasonable price.
Right. Yeah.
Aluminum, it's light. It can be very strong if you need it to be. We use it in aerospace applications all the time. There are versions that are compete with some of the other materials for some of the strength properties. But it's not a high temperature material. You lose your strength, and the surface temperatures are much lower. But it can be anodized, right? Anodization is a coating. There are a couple different grades. If you've seen anything that's brightly colored, is probably a type 1 or type 2. It takes pigment exceptionally well. You can load things like Teflon into the anodization coating to create your pans, for example. Or there's what's called type 3. It's if you see something that's heavy duty, that's that black, very durable anodized coating, that's a type 3 type coating. Magnesium works the same as aluminum for a lot of things, but it's a little bit more expensive and even lighter. So you might see it in alloy wheels or very limited applications. It's tougher to process. Titanium, right? It's sexy. It's light. It's got a high strength to weight ratio, so strength per pound is high. It's used some in aerospace, but mostly in places where you don't see it. Superalloys are, think of them as super stainless steels. That's what they evolved out of. Again, you're looking at aerospace applications or oil pipe. Copper is almost never heat treated. Not really, not in the same way where you're heat treating to bring out, the best properties. It's used a lot at room temperature. It's easy to work. You have great thermal and electrical conductivity.
About thermal and electric conductivity, are they the same thing? I understand they're not the same thing, but let me ask that differently. If something was very conductive of heat, would it be equally as conductive of electricity? Because I know that aluminum is as well. And at one time,
not necessarily, but
no.
So there are two methods for thermal conductivity. I'm gonna try not to jump into some super technical stuff on you, but electrons are able to carry some of the thermal conductivity. So something that's electrically conductive is also pretty good thermally. However, there's also a a phonon. There's a thermal type particle. So I don't want to get it.
That's
If I
okay.
start digging into it, there's another piece of the term. So it's the thermal conductivity is electrical and phonon conductivity. So if it's dominated by electrical conductivity, by electrons, then it's pretty good at thermal. There are materials that are light on electrical conductivity, but higher on the phonon conductivity. So,
Okay.
Without getting too deep into the weeds there, it's not a coincidence, but it's not the whole story.
Okay. Okay. All right.
So, aluminum and copper are great at both.
Yes, exactly. And very similar too, like in their makeup, it seems, other than the coloring, of course. But and why is that? They're both somewhat light. Copper's heavier, but they're if you've ever cut into them or cut them and turned them into chips, it's very similar.
Yeah. Well, the periodic table is not a lie. There's a reason why it's organized the way it is. Um, Aluminum aluminum's kind of an interesting place on the periodic table over with the kind of the metalloids. But I think the better example is to look at what's right below copper, and the answer would be silver and then gold.
Right.
So both great conductors as well. You don't hear about them because no one's going to make gold or silver wires unless you're going into space or something.
Right. Right.
Again, there's something material selection wise, right? So gold and silver just as good thermal conductors and electrical conductors as copper, and they don't tarnish. So there's no drop in resistivity, in the increase in resistivity there from the patina. But unless you need your material to not tarnish or
Yeah.
then you're not going to use gold and silver. But you look at the periodic table, right? So they're all right in a line, and they all have very similar properties. They can be drawn to wire very easily. They're very ductile, somewhat soft, right? So the periodic table is not laid out in order of discovery. There are a whole number of trends and properties that you can intuit from where it is on the table.
Okay.
Has to do with the atomic structure and a number of other things. But the way it's laid out, there are trends, certainly, if you know where to look.
Okay. Very interesting. Thank you for that. I will look more in depth for the relationships.
Yeah, things like electronegativity, size of the atom, all follow basic trends. The groups are vertically, so you have alkali metals, alkali earth metals, halogens, noble gases. They all share relationships. Chlorine, bromine, and fluorine are all in a line, and it's no mistake that they all fulfill similar functions.
Right. So I'm just looking at it right now.
So from basic materials, right? So we talked about kind of a couple different groups in the big ticket functions of different metals. The next part of material selection that's important to keep in mind is processing. You've picked your material. Now, how are you going to make it?
Right.
So it's not just alloying, right? It's not just what alloy. I picked a name off a chart, right? I'm going to use Inconel 718, a nickel iron based alloy, right? Well, how am I going to make it? So some things, a lot of commercial things, you can buy bar stock, you can machine it down, you're good to go, right? Other components, it's going to be forged or cast or rolled, extruded. There's a number of processing steps. How does that change the material? Do I need to do other steps to get it back to a state that I want? If I'm doing forging or casting, am I going to have to juice the master metal to change the composition? Am I going to have to reheat treat it? If I bought bar stock and welded it, am I going to have to do some stress relief afterwards? If I need to really change the shape and roll it down to a sheet, what do I need to do there? And then after that, if it's a material that I need to strengthen via heat treatment, what kind of cycles am I looking at there? Is it in gas or vacuum? Do I need inert gas? If you're talking about titanium, you're doing everything in vacuum. There's no way it's no way you're seeing temperature in air.
Okay.
Titanium loves oxygen and will react very readily with it.
Okay.
If you see an explosion at a titanium plant, which happens, moisture got into the vacuum system and introduced some other material, some oxygen to the material and causes the problem. Right. So what are the processing that needs to happen, right? Because that's part of the material selection process anyway, is okay, I picked the material, but what condition? If you look at an aluminum alloy, there's going to be a whole series of letters numbers right after the alloy. So you might say it's 7075 aluminum, right? That's a precipitation hardened. We call it aerospace grade aluminum. Well, there's going to be a T or an H or an O and some numbers after it, and that's the temper condition. It's like in the U.S. those 4 digits on the zip code that no one else but the post office uses, right? So no one else but a metallurgist is going to use the temper designation, but it's there.
Okay.
So the material, it doesn't just stop at I picked my alloy out of a catalog and I called the supplier, said I would like some of this alloy, please. Then that's how it starts. But then I need to do all the things I need to do to make that final product, and that's all part of the selection process.
Oh, is it? Okay. Very good.
Yeah. What process am I gonna use to make whatever the thing I'm making is, and then heat treatment afterwards. Do I need to do finishing? Am I giving it to you in a as cast condition, or is it blasted, or am I polishing it? Is it being welded afterwards, machined? So it starts with what material to use, because that'll give that ends the processing will give you the properties. I could take the same alloy. So let's talk about, I dropped Inconel 718 as a name. I would have to look at the difference between the forged properties and the cast properties, because they're going to be different. The yield strength of a forging is going to be higher, a forged material.
Right.
Do I need that?
Yeah. So then as the guy doing this, do you have to document all this at the same time to make sure that when you move on to the next thing, it's repeatable?
Yeah. In our world, the designers are doing this. So in my past life in aerospace, right, we would get a blueprint with a part saying we want you to make this part. It's a casting, so they've determined it's going to be a casting, so it would come to us, and they've determined the material they want and the heat treatment they want to run. So at GE or Rolls-Royce, Pratt & Whitney, whoever else we were buying supplying the part to, designers who are typically some kind of mechanical engineer work with their materials departments to figure all this stuff out. So they have alloys they prefer to work with. Usually they're their own proprietary alloys. They have a lot of data on them. They say, we need to use Rene 88DT for this application. It has the right mix of properties that we want.
Mhm.
And that's going to require these heat treatments. So we're going to put that on a print. And so that comes to us with this is the material, this is the this is the heat treatment, this is the post processing needed. Here are the chemistry tensile requirements, maybe creep depending on your application. So here's a list of properties you need to hit. Here's the chemistry it needs to have after it's been made into a part, and there you go. Then you're off to the races. As a supplier, then it's your job to figure out how that fits into your process, how you can best make the part.
Okay. Yeah. So is there like a certification process though? I mean, when it's going onto an airplane, I mean, imagine that's pretty serious. I mean, I know it is. So is there certification for that? And
absolutely. Absolutely.
Yeah.
There are, as a company, you are, the big ones in the industry are, ISO certified.
Okay.
So you want an ISO certified process, you want a NADCAP certified process. So that's independent inspectors coming in and verifying that you have quality systems and run your processes the way you're saying you will.
Yeah.
That's when let's say Rolls-Royce is buying a part from my casting company, let's say, there would be a qualification process where there is inspections, parts that are cut up, for X amount of parts until we've proven capability, and then then you get periodic testing. So every X number of parts, you're doing more testing. So everything is qualified, certified, verified, before it becomes an actual part. All stages of the process.
Yeah.
And everyone's doing that, and traceability is the big thing. If a plane goes down, they're tracing components back to raw material.
Of course. Yeah. Yeah, they are.
So you find what batch of nickel came from wherever, and let's be able to pull out the certifications on that.
Yeah, we gotta blame somebody. Yeah. Fair enough. That makes sense. I lost my train of thought.
Well, material science and material selection are an important, but basic part of the process, right? Most of the time, even as metallurgist, I'm not involved in that bit, right? In working in industry, in the aerospace industry, that came to me, and sometimes we could say, well, we think with our experience that maybe this would work better, but a lot of times that's the person who's designing the part, that's where that part happens. But in a small shop, right? In smaller scale businesses, you have a machine shop who's making something, right? They're looking at what stock they have on hand, what they have experience with, and they may not know that maybe there's other materials that might be better for their application out there. But without knowing to ask that question, you would never know, right? Yes. Hey, we've made a ton of this in 1080 steel, so we're going to keep doing that.
Yeah, but that's not always the best, right? Because that's one of the famous sayings in business that can make a lot of things fail is, well, this is the way we've always done it, so let's just do it that way, right?
Yeah, it's all negotiation. Maybe the 1080 steels works fine.
It could be.
Could they get better performance for a marginal cost? Perhaps. But that's the name of the game is figuring out whether that's worth it.
Yeah.
I got a great deal from Joe down the street on 1080 steel, so we're going to stick with that, Or if we switch to 4340, we could make a much better part.
Yeah.
In
Well, and
you know,
it's also how many are you making, and I mean how much.
economies of scale is always important,
Yeah.
right? But this is what we're talking about. This is, you get out of industry and the answer is not always the best material. And that's what engineers have to learn is this negotiation,
Right.
with cost, with availability, with properties,
So really,
processing.
I mean, really, you're a consultant in a way. You're just specifically about the metal bit. Like you have to get to the bottom of what is it they're trying to solve, other than just providing a part. What's the part solving for your client? What's your client's goal with this part,
Yeah, I mean,
etc.?
for me, as an independent metallurgist, half of my job is telling someone, okay, you don't know what metallurgy is or that it has impacted your business, but it does. I promise you, and this is why you need to understand that.
Yeah.
And this is where it can come in and really change things. If you said you're a machine shop, you got this kind of bar stock on the shelf,
Mm-hmm.
and you're making these components. It's a great component. You're doing quality work, and I wouldn't tell you you're not. But you may be able to turn out a better part for not, by not changing your process very, very much.
Mm-hmm.
We just made a few metallurgical changes.
Yeah.
So yeah, that's where I'd like to come in. That's problem solving for me.
So ideally,
but,
what would that situation look like? Like, what are the questions you'd be asking to get to the bottom of the material selection? And
I mean, like your first question, right when we opened the podcast, did someone really make that choice as to what to use, or is it just it was what was there, or this is what someone told me? Is it a deliberate choice, and then why? What are the reasons? Maybe they're great reasons.
But it's making sure that they've been thought about, right?
Yeah. I mean, do you know why you're using this material? And what's really important about the thing you're making, and can we improve that? Because I think people do like quality, and cost and quality are two important things, and a lot of people are willing to pay for a better product. They're still selling Honda Civics, and they're still selling fully tricked out BMWs with F1 racing technology, right? There's a market for both. Which is your product fulfilling.
Well, and that's it, right? And it's a bigger question of like, what is your market? What is your play in the market? Are you just competing with another person that's making the same commodity, or are you doing something a little unique like the F1 car or Ferrari, right? I mean, it's where are you positioned? There's a lot to the little thing, the little widget. There's so much to it, right? To their positioning in the market, right?
I mean, that's why these material selection in business and industry is so much more complicated than material selection in my senior design project.
Yeah.
And why it's more important. But that's the things you learn along the way. That's being able to take the things you learn in school and the things you learn out in industry and apply it all to someone's problem. I mean, that's what engineering is about. It's hard problem solving.
You're a professional problem solver, absolutely.
Yeah, absolutely. I just specialize in metals.
That's right. It's good to niche down anyway.
I enjoy it. It's like I said, I was a metallurgist from an early age. I just didn't know it.
Yeah. Cool, man.
Trying to figure out what my lacrosse shots are made out
of. You'll figure it out.
Yeah.
And maybe they've probably thought a lot of these things, the schools and whatnot. It's just you can't totally prepare anybody for the real
Oh,
world,
absolutely,
right?
absolutely not.
You can't. So, I mean, you just give them the best information you can, and then you say, okay, well, he's going to go out and figure it out on his own because everybody has a different path, right? So, you could be in school forever, but
Nearly a decade for me, but
but you can't learn it all there, right? I mean,
no.
you've learned a ton, I'm sure, a lot more than I did because I didn't spend any time there.
I
But
like to, I have a PhD, and that can be off-putting for people in a job when I'm applying for jobs. When I have applied for jobs in the past, if someone needs my skills, then absolutely, I'm a round peg in a round hole, right?
yeah,
But all it really means is that I spent a couple years trying to solve a specific problem. I know a lot about that specific problem, but what I also know is how to set up and delve into a problem, right?
yeah, yes,
How to I'm given a question. What get to the heart of that? Do the research, do the testing, answer that question, right? That's all that some of these advanced degrees are. Um, so yeah, at one point I was the I wrote my thesis on additive manufacturing, the repair of additive manufacturing materials, right? In a superalloys in an aerospace environment. So when I presented my thesis, I was the expert, right? I had done all the research. I had done, that's the thing they tell you when you go defend your thesis is like, remember, you're the expert. They're asking the questions, but you know, if you did it right, you should know all the answers because you did all the research,
hmm
all the testing, all everything like that. So you're the expert. And so for that thing, I was the expert. But now for me, what it means is that I'm comfortable taking a problem and maybe I know some of the answer, maybe I don't, but I can go research that
yeah,
and I can put it together into a coherent problem statement and analysis and an answer and get that back to you, right? That's what
yeah,
that
man.
means to me is that
I think
I
that's a good position on it, man. It taught you how to solve a problem in a critical way, in a critical thinking way,
yeah,
and learning how to learn and how to present that, right? That's important, especially.
it is, and that's so when you're looking at someone across the interview table and they have an an advanced degree or are very specialized, sometimes all that means is that there's some specialized knowledge, but maybe some good methodology there, that maybe some a lot of good experience.
Yeah, yeah, agreed. Cool, man. What's the worst case scenario for material selection? Like,
Um,
what would be your nightmare?
the I don't know, the Tacoma Narrows Bridge comes to mind. Um, no, I mean, look, there's a lot of stuff out there. Um, Sometimes very rarely is it malicious. Um, Oftentimes it is something that's not quite understood. Um, hey, we don't know that. I'll use the Titanic as an example.
Okay.
It was made with the best metallurgical practices of the day, widely accepted, but the steel wasn't very clean, and they had different, each of the supposedly, impregnable, steel bulkheads, right, had different properties because they didn't have a very clean or repeatable process. Um, they had 3 million rivets, and most of them had slag in them, and the rivet heads would pop off. The the steel practices, which, like I said, it wasn't bad steel. It was good steel for the day.
hmm
But they didn't know how to test their steel to see if it all had the same impact properties. Um, the temperature of the ocean at the time put the steel below its ductile brittle transition temperature, and
Jeez.
the impact loading running to an iceberg even more created brittle behavior. Um, so that's it's a perfect storm of things that created a tragedy.
Yeah. Yeah.
There's a great report. They actually, when they dove on the Titanic in 1991, they brought back metallurgical samples. So people ran testing on some of the stuff. Again, it's not bad material selection. The steel was the best choice, but maybe the processing wasn't quite right. The testing, testing and verification, like we talked about, was not up to not what we would do nowadays.
Right.
Right. So you're going to make it out of steel, but could they have done different steel, cleaner steel? Yeah. And most people don't make intentionally bad decisions, but these things happen. But that's why we have processes, testing, all these things to protect us from life happening.
That it does. Yep. Good answer. I didn't know where you were going to go with that. That was good.
Thanks, Greg.
It's a hard answer, though. I mean, it is, because you don't know. I mean, how do you even? You can't predict the future. So the nightmare scenario, I don't know where you were going to go with that. So, cool, man. So what else do I got to ask you?
I mean, I think we've covered material selection in a practical manner, from the schools to industry.
Okay, cool. Any advice for anybody when they're going to choose the right material that may be counterintuitive to their conventional wisdom?
Yeah, I mean, I would say keep an open mind. There are a number of tools out there that will, there's never a better time to be looking at this stuff, because there is a lot of information out there as to different properties of the stuff. There's, it used to be you had to have the right book, maybe a big ASN handbook sitting on your shelf, or working in industry. But nowadays you can find some good thresholds and ideas for things online, and go from there. But I think the most important part, again, is really figuring out what's the most important part of your product. What is the thing you need? What's the deal breaker? And then what's your cost threshold to get there?
Yeah. Yeah, absolutely.
There'll always be a slightly better material. But it may not be worth the marginal cost.
Yeah, and that's the thing about, it's like anything in life, going back to the other question, like what's the worst case scenario? And I'm having a hard time getting my thoughts out because I'm really tired for some reason. But I guess what I'm saying is conventional wisdom is almost always wrong. And when they were making the Titanic, and that's why I complimented you on your answer, because they were doing the best they could with the information they had, right?
Yeah.
And and that's all we can do today too, right? And it's hard to fathom the worst case scenario, but there are a lot more systems now in place than there were then, and then we will continue to do that, right? So do you think there's what kind of ways can we improve you'd mentioned something earlier, and I don't want a blockchain, everybody brings it up, but I'm curious of if there's any thoughts around the verification process of raw materials or widgets, for example, to verify that they're real, that to eliminate a lot of the garbage in, garbage out stuff.
I think this is where the digital world and the physical world kind of diverge a little bit. It takes a lot of effort to make some of these widgets and to make some of these raw materials, and it's less so that I'm worried about counterfeit materials, and more that I'm worried about, let's talk about raw materials, that it's not as pure, or there's impurities in there that are not documented.
Okay.
From a raw material side, from other materials, from a physical widget side, I want the chemistry to be what it's supposed to be. Is it really this alloy within these, within this compositional range? Does it have the the properties that it's supposed to? Did it hit 150 KSI or whatever threshold you put on it? The thing you start thinking about is, again, this is something, in a problem on a materials exam, I'm given a composition, for example. Okay, those numbers do not represent every spot in an ingot or in a bar that I bought, right? It's in a range.
For sure.
It depends on sampling. It depends on, we use a lot of statistical sampling and statistical process in industry, because do I need to take 3 samples? Let's say I get a ton of nickel briquettes in. How many samples is a representative sample? Is it 3? Is it 5? Is it 10?
Exactly. That's hard to know. I mean, it's so random.
When a problem happens, well, that's why the systems are important, because my system says I need 10 samples. If I took 10 samples and everyone agreed, the people buying my parts that are going into the plane that are, if our system is documented and say I need 10 samples, and all the samples I took are documented and good, there's variability in everything. So my 10 samples weren't representative, but I determined that 10 samples should be representative. You see the distinction there is that there's randomness, there's things that are always going to happen.
Mm-hmm.
But if I stick to the systems that I put in place that are, guarantee that are, effective 99% of the time, right? That 1% is going to happen, but I'm controlling that, right?
Yes.
We talk about driving to 0 defects or something in that manner, and that's not really reasonable, right? We're never going to be perfect, but striving to minimize the number is a great strategy, right? So something's always going to happen, but the reason why planes are safe is because there's systems in place every step of the way to prevent random occurrences from happening. So if I have sampling in place to make sure that my raw material is up to snuff, and then I have testing in place to make sure that the material I'm producing from that raw material is what I think it's going to be, and then I have testing in place to ensure that the parts I'm making from the metal I supplied are hitting the properties I want, and and the designer built a safety factor in. And then when it's put in a plane, there's periodic inspection criteria where if it doesn't meet inspections, it's taken out of service. And, then there's built-in pilot procedures to deal with, engines going bad, right? So there's safety every step of the way. And that's what ensures that air travel is as safe as it is.
Yeah.
So bad things are going to happen. I saw a great talk by, Sully's co-pilot from, the Miracle on the Hudson, and, things went bad very quickly, and there was not really anything to recover from. But they, if you listen to the cockpit voice recorder, they were calm. They were walking through checklists and procedures, evaluating, discarding options, and then the best option was to land it in the Hudson, and then use all the safety systems built into the plane to safely evacuate all the people and get them under shore. So again, you can consider that a failure of the plane, but it's a triumph of all the systems, all the safety systems.
Yep.
One thing went wrong, and then a bunch of things went right that they had trained for to make sure that we got the best outcome.
Yeah, I agree. I believe in systems, and I believe in having all that measured. And I mean, those guys have practiced that so many times that clearly it works. To It's like anything. Like I've been thinking about this, like about presentations and stuff, and it's like, what was I watching? I was watching this thing about Broadway actors, and they were talking about like getting into the role, and it's always about the practice. And then you get past the point where you need the practice. You've done it so much that you start making it your own thing. But it's very similar to what these pilots are doing. It becomes second nature, right? Where they
Absolutely.
just, right. And same with the systems that you put into place in your business or in the scientific community or my business. Those just become routine. And, it really can affect things positively for people's lives, number one, and then number two for um so many reasons, like making profit, or if I die tomorrow somebody can continue on with the things that I do, or whatever it is, you know what I mean? So I'm a big believer in that.
It's important, succession planning in your life and industry,
Well, not
and
even just that, anything, right? Like
yeah.
it's so um yeah, man.
The
That
last
was
thing I would recommend is that there's a documentary about the Boeing 737 Max thing that if you
I would
it's
love.
called The Downfall of Boeing. It's on
Oh,
Netflix.
I've seen that. Man, oh
It is a
man.
really great discussion, and the second half kind of focuses on Boeing, and
And
I
how they
think
came
that's
and how
sorry.
they came out of it, right?
Yeah, and the really how they got to where they are because Boeing has such a reputation for um, had a reputation for engineering driven decisions
Yes.
and where they are now and how they got there. And I think that's a really great watch again for anyone coming out of school or wanting to see a practical view into these kind of industries. Um, that Boeing story is not unique in I would say in industries
There's a lot of
with
similar
the
stories. Like the General Electric has one that's kind of similar. Like this one was around the tail issue, right? The tail wing, that
yeah. I mean
something
even just
locked, right?
there was a system that they put in place to deal with an engineering issue, but
Right.
the system wasn't well documented and pilots didn't know about it.
Yes.
Um,
Yes.
so that was the technical issue, but I think the response and the culture issue at Boeing is also a really important watch for anyone who is in a technical industry
Mhm.
and as a a cautionary tale.
Absolutely. And I think taking responsibility for things is key. You make mistakes, we all make mistakes, but it seems that once the you get to a certain echelon in these large corporations, you become you have this power. I don't know what happens to these people. I've never been one of them, but they become arrogant and they can't admit their faults, and they can't admit well, I don't know what it is, but that's what the culture becomes, where you just push the blame on somebody else, or push the blame on this or that or the next thing.
Yeah, and
When,
there's a great discussion about that. How
yeah,
engineering culture to management culture.
yeah,
Um,
yeah. And it
it's important. It's
happens
important.
all the time.
Yep.
So, but there's another great one if anybody's curious. This is more around finance, but there's Carl Icahn. He was involved in a lot of these types of things, and he is known. I would call him as a shareholder activist more than a corporate raider. He gets those
Okay.
two titles in different places, different circles, but his main mission, as I see it, is caring about the shareholders in the company, right? The shareholders being the average person, not the management. And he runs into things like this too, where it's like this company is way too top heavy, everybody's too arrogant, you people need to get your shit together, and this is why. And he made a ton of money doing that, but it's really kind of a great parallel to the one you're talking about, Boeing.
Yeah, I mean, again, we're talking this, we've been talking about practical sides of engineering and the technical side. There's the what's the best technical material, but then what can we produce? What can we afford, and what's the best for our product and our process? I think culture-wise, you get into the same sort of things.
Yeah, man. Yeah, it's all like it's a living organism, right? All of it, a business and everything it makes, and the people and the culture. It's like the thing that it makes is like one part of it, obviously, right? There's so much more to it. Anyway, it's been a pleasure, my man.
It's always great. I love our discussions. So
likewise, and we'll be in touch soon. And have a good one.
You as well, Greg.
Okay, man. Cheers.
Greg Sheldon here, your host of Metal, Steel, Manufacturing, and Business Pro podcast, where you learn everything about the metals and manufacturing industry that make your modern day life possible.